Okay, so today what we're going to discuss is we're going to discuss the mole. Now, since you've read your article, you should know that the mole is equal to Avogadro's number of something. And Avogadro's number is 6.0221 times 10 to the 23rd. And I think the article actually gave you some extra decimal places out here, but they're not necessary because most of the calculations we do in class, these 5 significant figures here will be plenty for what we need. So the way I would like for you to think of the mole is the same way that we think of a dozen. We know that 1 dozen items equals 12 items. It could be 12 of anything. It could be 12 cars or 12 roses or whatever else we would have 12 of. We just understand the relationship of a dozen to 12 items. And so what we need to see about chemistry here is that in chemistry, the mole means this many of something. And that something is molecules and atoms. In fact, it's only really practically applied in chemistry to something molecules and atoms because this is such a massive number. And with such a large number, if you're not counting something really small like molecules or atoms, then you have so much of it that it's just really difficult for it to be practically used for anything that's not really small like a molecule or an atom. So what we really want to be able to do in chemistry is we really just want to be able to convert between the two. And so the way that we'll start this off is we'll do a conversion with the dozen to give you an idea of what we're looking at here. And so let's say that we had 2.5 dozen roses. And for some reason, you wanted to know how many individual roses that is. Now, I understand you all are smart enough to take this number and multiply by 12 and figure out how many roses we have. But we're going to use a little dimensional analysis to introduce the concept here. So 2.5 dozen is our known value. And that's going to be in the numerator. And so what we're going to put down here in the denominator is dozen as well. If you remember from when we did this earlier in the semester, we wanted to make these 2 units match in the numerator and the denominator so that they could be crossed off. And we know that 1 dozen is 12 roses. And so, of course, our dozens cross off, and our answer is 2.5 times 12, which comes out to 30 roses. So we were able to use a one-step dimensional analysis problem to multiply 2.5 times 12 to give us 30 roses. So let's look at a similar problem, except for this time, instead of using the dozen, what we're going to use is the mole. So let's say we were presented with a problem, 2 moles of copper equals how many atoms of copper? Okay. Now, really, it wouldn't even matter what it is. It could be atoms of copper, atoms of nickel, molecules of water. It's all the same because remember that this relationship here, moles, is just a counting unit. 2 moles of anything is always going to be the same number, whether it's 2 moles of copper or 2 moles of any other element or compound. But anyways, what we'll do here is we'll start off with the known value here, 2 moles. And so that's going to be the first thing that we write in our dimensional analysis. We have 2 moles of Cu of copper. And we know to do this correctly that we're going to need the same unit in the numerator and in the denominator. And so we're going to put moles of copper down here so that at the end of this problem they will cancel. And we want to go from moles of copper to atoms of copper. That's what we're trying to convert to. How many atoms of copper, are in how many moles of copper? Well, we already know the relationship here. 1 mole is equivalent to Avogadro's number. That's 6.0221 times 10 to the 23rd. And so now what we have here is we just have a math problem, just a multiplication problem. Our moles of copper cancel, and our units will be atoms of copper. And now we just have 2 times 6.0221 times 10 to the 23rd. And that equals, okay, let's bring up our calculator. And we're going to put in 2 times 6.0221. And we get 12. Where'd it go? Where'd it go? 12.0442. So 12.0442. Now, notice that we didn't include this part in the calculator, and that's because really if we see this number as 2 times 10 to the 0, this is just like multiplying scientific notation. So we multiply the 2 by the 6.0221, and then of course 0 plus 23 is just 23, and so we tack that onto the end here, times 10 to the 23rd. And there's a couple things that we still have to do here. First, this is not a correctly rounded number. So let's go back to our numbers here and look. So this one, as we had already established, this has 5 significant figures. Okay, the 6 and then the 4 digits afterwards. And this 2 over here, this has 3 significant figures. So our final answer should be rounded to 3 significant figures. And we're just going to count over 1, 2, 3. So we're going to look at this 4 to determine if we're going to bump up the 0 or if we're just going to leave it alone. And of course a 4 drops off. And so to correctly round this, we're just going to round this to 12.0 times 10 to the 23rd. And this is not correct scientific notation, so we need to move this decimal over and make this 1.20 times 10 to the 24th. Moving the decimal place over to the left will raise this number by however many times you move it to the left. And of course, if you moved it to the right, it would decrease that number by that many. So our final answer is 1.20 times 10 to the 24th atoms of copper. Okay, so what if we want to go the other direction? What if we, that was a scenario where we converted moles to atoms. But what if we started off with atoms? What if we had a scenario where I said, well, you have 1.30 times 10 to the 25th molecules. We'll go with molecules this time. It's the same as atoms in this sense, of water. And we wanted to know, well, how many moles of water is this? How many moles of water do we have? We want to go from molecules to moles. Well, again, we start off with the number that we've been given here, and we put that one in the denominator. So 1.30 times 10 to the 25th. This would be molecules of water. And we know from dimensional analysis that we have to put molecules of water in the denominator because we want to eliminate the unit molecules of water. And then we're going to put moles of water in the numerator because that's what we're trying to convert to. So how many molecules of water are there in 1 mole of water? Well, it's Avogadro's number. There are 6.0221 times 10 to the 23rd molecules of water in 1 mole of water. So molecules of water cancel, and we're left just with moles of water. And now we have a division problem. 1.30 times 10 to the 25th divided by Avogadro's number, 6.0221 times 10 to the 23rd. Now again, if you remember from the beginning of the semester, we discussed how to divide scientific notation by hand. And so what if you recall, we said that we are going to divide the coefficients, and then we are going to subtract the exponents. So the subtracting of the exponents is pretty easy. 25 minus 23 is going to be times 10 to the 2nd power. But we're going to use a calculator for this other one here just to make life easier. So we're going to say 1.3 divided by 6.022. my mistake. Oh boy, I have to clear this out. 1.3 divided by 6.0221. Enter. And so we get 0.21587, and that's enough digits to remember. So we'll put that down here. Oh, there goes my old age brain again. 21587. 21587 times 10 to the second. Okay, and so there's a couple of things here, just like with the last problem. One, this isn't rounded correctly, and two, we still don't have it in correct scientific notation. So let's address that last problem first this time. Let's get it into correct scientific notation. Our decimal is here, and we're going to move it over just 1 to make this number between 1 and 10. So now we have, instead of 0.2, now we have 2.1587, and we already said by moving it to the left, we're not going to increase this number. By moving it to the left, we're going to decrease this number, and so now this drops down to 1. So let's rewrite this over here. 2.1587 times 10 to the 1 power. And now we need to go back and look at Sig Figs. So we go back to our numbers here, and we see again this version of Avogadro's number that we've used here has 5 significant figures. And this number here only has 3 significant figures. And so our final answer will be rounded to 3 significant figures. And so we count out here 1, 2, 3. That's the one we want to look to. Now we ask ourselves, will an 8 bump the 5 up to a 6? And it will. So we're going to round that up to 6. So 2.16 times 10 to the first power. And of course our unit is moles of water. Now if you're wondering why we left it in scientific notation, it's just because we calculated it that way. It's perfectly acceptable to go ahead and move the decimal that extra 1 and just go ahead and call this 21.6 moles of water as well. Both answers are acceptable. Scientific notation or a decimal is fine. My only caution with a decimal is if it is a really large number, say above the hundredths place, you may want to leave it in scientific notation just to keep it nice and compact, and you're able to show exactly how many significant figures you have when you report a number in scientific notation. So for this video, what we showed you is how to convert, if given a number of moles. Let's erase what we got here. So what we showed you, if we were to set up a little thing here, is we showed you that if we gave you a number of moles, we showed you how to convert to particles. Okay, and we've defined those particles. Those particles are either molecules or atoms. Okay, and then in the second part of the video, we showed you how to go from particles like atoms and molecules over to moles. And so you'll notice that the conversion factor that we're using each time here is Avogadro's number. If we want to go from a number of moles to a number of particles, we're going to end up multiplying by Avogadro's number, 6.0221 times 10 to the 23rd. And if we want to go from a number of particles to a number of moles, we're going to divide by Avogadro's number, 6.0221 times 10 to the 23rd. When we set up our dimensional analysis, we'll end up dividing. In the next video, I would like to go on to explain how we go from a number of moles to something we can use practically in the sort of the macro world, sort of the world in the lab where we can actually measure something. And so we want to go from a number of moles here in the next video to a mass in grams. And so what we're going to discuss in the next video is how are we going to convert from moles to mass.